All right, welcome to Unit 1, Exploring One Variable Data. Today's topic is over 1.6, describing the distribution of a quantitative variable. In the previous video, we talked about graphs of quantitative variables, and I brought up talking about its distribution. Now we're going to really kind of dive into it more specifically. So when you describe the distribution of a quantitative variable, there are three key features of that distribution you have to examine. Now remember, distribution is what values your variable takes on and how often it takes on those variables. So to describe that in the most detail, you need to mention the shape of your distribution, the center of your distribution, and the variability or spread of your distribution. A fourth item is outliers as well. If you see them, we'll talk about that too, but the main three are shape, center, and variability. Let's talk about shape first. So once you have your quantitative variable graphed, you'll see a shape. Whether it's a stem plot, a dot plot, or a histogram, you'll see your data start to take on a shape. There are a couple key shapes that you'll often see. The first is what we call skewed right. A skewed right shape is or it's also known as positive skew, is when the right tail is longer than the left. In simple terms, it just simply means that there is more data on the left, less data to the right, hence skewed to the right. So again, skewed to the right is less data on the right, more data on the left. So again, we say that the right tail is longer than the left. And in fact, there is really only a right tail. So if you look at any of this data here, there's a tail. So we kind of make it almost looks like a dinosaur's tail or something like that, right? Okay, so here are three examples of skewed right. The first two are histograms, where you see there's more data over here on the left. And then again, there's no numbers here, so it's kind of more vague, but you'll see that the data starts to get less and less and less. Now here's a little bit more specific one. We got some data here with some numbers, and we notice there's lots of data. This data went by fours, right? 0, 4, 8, 12, 16, so forth. There's a lot of data from 4 to 16, tons of data here. Look how high these bars are. And then again, as we get higher and higher, there are some values, some individuals, but not many, very few. Here's another one that you could see now with the stem and leaf plot. You almost have to kind of turn your head to the right? Turn your chin to the left and your head down. Anyway, and what you do is you see the skewed right. So the idea here is that the numbers go bigger, right? So 150 is much bigger than 34. So these are the bigger numbers, and there's less of those, right? Most data falls down here in the 50s, 60s, and 70s, and the data kind of goes to the right. So what you could kind of do is you could kind of give like a quick little like, all I'm doing there is kind of make a quick curve over top of my data to kind of show that tail there to the right-hand side. So the data is tailing off to the right, hence skewed right. So obviously that means we also have skewed left. Again, what's happening here is the data is skewing or tailing off to the left. So this is also known as negative skew. This is when the left tail is longer than the right. So the left-hand side is longer. So again, if I make that kind of quick little curve, I see that there's a tail to the left. Same thing in this picture right here. Again, going by 4s, 8, 12, 16, 20, and so forth. I see that there is more data to the right, less data to the left. So very few values, 8, 12, 16, 20, 24. Most values were higher, 40, 45, or 44, 48. That's where a lot of values were falling. So those are two really important ways to describe shape. Another way is symmetric. Oh, I skipped that. Sorry, here's symmetric. Another way is symmetric. A symmetric distribution is when your left half of your data looks pretty close to the right half. So in this first example here, we almost see two tails. We see a tail to the left and a tail to the right. So again, make a kind of quick curve there. You see that there's a lot of data in the middle, and then there's less data to the left, and there's less data to the right. Here's another very nice example of that. A lot of data between 40 and, 40 would be right here. Not 40, 40 or whatever. You get the point. A lot of data up here, and less data as we move to the right and when we move to the left. And this would be a 42 right there. Sorry about that. So again, you see there's more data in the middle, less data on the sides. But there's not a predominant tail, right? Like skewed right is when there is a huge tail only to the right, or skewed left, huge tail on the left. Got a tail on both sides. That's going to be symmetric. And again, here's another example of a really good example. It's different than the other two, but it's still symmetric, right? There is very little data in the middle. Most data is on the left, or most data is on the right. Now, it's not perfect. And the other thing I want to mention is none of this is going to be perfect. You're never going to see perfect mirror images left to right, but it's somewhat, right? So if we look at this last example here, we do see that it's somewhat symmetric in the sense that the left side somewhat mirrors the right side, but just a different way of being symmetric, but it's still symmetric. We can also talk about shape in terms of peaks, right? So these are all symmetric, but you wouldn't just use the word symmetric because they're all symmetric, but yet they're all very different. So this one here on the left, you would say is unimodal because it has one single peak, right? There's a couple that are pretty big, but you have one main peak, one main area where the data seems to be centering. That's going to be unimodal, unimodal meaning one. Now this data here is also symmetric. The left side and the right side kind of look the same, but we'd call that bimodal because we have kind of two big peaks where the data starts to be clustering together, and that's what would be bimodal. Now this here is also symmetric, right? Again, all the bars are in here. Imagine all these bars in here. I don't know where those lines went, but anyway, you notice that the left side and the right side, in fact, the whole darn thing looks the same, so that would still be symmetric, but we would call this uniform, where there's about the same number of individuals in every single bin. Now, you're very rarely going to see it ever be perfectly uniform like this. You might see it'll be a little higher here, maybe a little bit like this. But the point is that there's no tail. There's no big tail left or right. It all are about the same. So we have these words, skewed left, skewed right, symmetric, and then we can add words in like unimodal, bimodal, uniform if you need to better describe the shape that you're seeing. For example, I would never just say symmetric here because that doesn't really tell the whole story. I'd say symmetric and unimodal. Here I'd say symmetric and bimodal. If I go back to some of these skewed graphs, this graph right here on the right would be unimodal and skewed left, obviously. Now, some people would say, well, wouldn't this be bimodal? There's two big peaks right here. Yes, but they're not separated. They're pretty much close to each other where they're not separated, right? Bimodal is more we have these two completely separate clusters or chunks of data. So these are all the different kind of words I should be seeing when I ask you to describe shape. Unimodal, bimodal, uniform, skewed left, skewed right, symmetric are kind of some of the more famous words that you'll be hearing. All right, let's talk about center, right? Now we've talked enough about shape. Let's talk about describing the center of our quantitative distributions. So when you talk about center, you're really looking for one value that you feel best describes the data, right? Don't worry about calculating anything yet. We will eventually. But right now, we're just thinking about one value that you feel best represents your data. So let's talk about these two graphs. So on the left here, I have a back-to-back stem plot, and it represents males on the left, males on the right, females on the left. And each individual, we asked them, how many pairs of shoes do you own? And they gave us a number. So, for example, the key says 2 would mean 22 pairs of shoes. So, for example, this individual only had 4 pairs of shoes. This individual right here had 38 pairs of shoes. Make sure you don't read that as 83. The middle is the stem, the beginning, 38. So anyway, if I were to say, all right, what's the center for the females? What's a very common amount of shoes, center, for the females versus the males? Well, for the males, I'd probably say something like 7 pairs of shoes. That's a pretty good center. It's definitely got some less. It's got some below. I mean, again, there's no right or necessarily wrong answer here. If you said 8, or if you even said 10, again, 7, 8, 10, those are all good examples of the center. But just give me one number. If you said 38, 38's the max. 38's not the center. That's clearly wrong. But 7, 8, 10, those would all be roughly where the center is. As of right now, I'm not going to say you're wrong if you gave one of those numbers. For the females, it's much higher. For the females, I might say something like 26 pairs of shoes would be the center. Some lower, some higher. But if you're a female, it's 26. So it clearly shows that females, you typically have more pairs of shoes than males. So that's the nice thing you could get. But again, I'm just trying to find a number that represents the center. Now over here, we have the discoloration rating for strawberries. So we looked at 2 groups of strawberries. 10 is that they're very discolored. You don't get a bad strawberry. It's like black, green's gross. And then, 1 would be perfect. 1 would be a perfect red, nice, no discoloration at all. So if you look at these 2 groups and I said, hey, what are the centers? For group A, you might say somewhere around 5 would be a good center. For group B, I'd say, well, group B might be a little bit more discolored. Their center might be somewhere around 7. It's kind of a center of the data, half below, half above, kind of idea. So, I don't know what's going on with these two groups of strawberries, but I'd say I'd rather eat a strawberry out of group A. Now, does group A have some bad strawberries? Yeah, but group B has a lot more bad strawberries. So again, that's why the center for group B is a little bit higher, more discolored. I'd rather have a strawberry from group A. But against this idea of trying to find a value that represents the center. That's usually pretty easy. All right, spread. When we talk about spread or variability, we want to get a sense of how the data varies. So here we're looking to talk in simple terms about the range of the data, you know, what's the smallest, what's the highest, but we're also talking about where the data is at. I kind of think about putting butter or jelly on my toast in the morning. You know, do I spread it nice and evenly to the corners and all over, or do I put one big clump in the middle and most of my bites don't even have any jelly on it at all? So where do I spread out that data? What's the variability of that data? So here is an example of a bunch of values. There's really no context here. In fact, I don't even have a key. I should probably give you a key real quick. Let's just do a key like this. 8/9 would mean 89. Now, no units here. It's just kind of vague, generic problem. But, you know, when you look at this and you want to talk about the variability, the first thing I notice, there is data here. I'm so sorry. I should know my own presentation, you would think. These are heart rates of patients, right? We took the heart rates of several patients. So this would be 89 beats per minute. That's their heart rate. Okay, so there is context here. So the first thing I noticed is that the data ranged from a low heart rate of 68 to a max heart rate of 168 while exercising. But the other thing I noticed is that a huge chunk, an enormous chunk of patients where somewhere around 110 to 140, 130, you know, in that range, 110 to 140 is where a huge chunk of people fell. So if I'm going to talk about this variability, I'm going to say the variability of the patient heart rates were from 68 to 168, but the large majority of patients had heart rates from 110 to 140 beats per minute while exercising. That's a great answer, right? Here's what's going to happen when I give you guys your first big test, your first big quiz. You're going to say, oh, the heart rates were from 68 to 168. Don't forget units, beats per minute. And that's not enough, right? Give me some more context. The variability of the patient heart rates, talk to me, was from 68 to 168, but I noticed that a large majority, you can even count how many of you want, large majority of patients were from 110 to 140 beats per minute. This is talking about your data. You're describing how the data varies. Now, while we have this graph up here, we might as well mention shape real quick. So kind of tilt my head. I think this is actually a little bit skewed left. I do see a tail to both sides. There is a tail over here and a tail over here, but it does look like that left tail's longer. So you can even add an adjective in there like slightly skewed left. All right? It's not exactly symmetric because that left tail's kind of noticeably longer in my opinion. So I'd say slightly or a little bit skewed to the left. What's the center? Looks like anywhere around 127 to 130 would be a pretty centralized heart rate for this group of data. Again, I know I'm being a little bit vague right now, but I'm just trying to get you used to talking about three things. Because on a test, on a quiz, you got to talk about these three things: shape, center, and spread. All right. It's also really important that when you talk about shape, center, and spread, you talk about being able to compare two different distributions of the same variable. So here's a great example, and we'll just kind of run through it real quick. In this data plot right here, what I did was we had catapults, right? Everybody knows what a catapult is. You pull it back maybe with the rubber band and you launch a ping pong ball or something up into the air. So we have two catapults, and each of them we rocketed 40 ping pong balls out, right? And we measured how far the shot went, how far we shot that ping pong ball. And for catapult A, here's all of our data. Catapult B, here's all of our data into these nice dot plots, right? So what do I notice here? Well, I notice shape. They both look fairly symmetric, to be honest. Not perfect. Catapult A has a tail on both sides. They look fairly symmetric. Catapult B doesn't really have a big tail on either side. You know, the left side looks to be a little bit more spread than the right side. But again, it's nothing major that I would say, oh, that's so skewed. It's pretty symmetric. So that's a similarity that they have. You could talk about their centers. I think the centers are a little bit different. Now, you got to take all these values into context. Don't forget about these extremes all the way out here. I would say the center for catapult A might be somewhere right about 135, 136-ish. And then catapult B does appear to have a center slightly higher. And if I'm going to try to grab a center, it might be somewhere right around here-ish maybe. So that'd be about 137. Right here's 135, 136, 137, 138. So 138, 137, 138. You could even give a decimal, 137.5. You know, somewhere around there would be the center. So I don't care if it's a slight change. It's still something worth talking about. A is around 135. B is around 138 centimeters. Now I could talk about spread. And I think spread is where we see the biggest difference between these two distributions. Catapult A is spread from very low, maybe around 120, all the way to very long, 155. Yes, most of the data in between goes from about 133 to 137 is where there's a big cluster of data, but it's very spread out. This catapult A was not the most accurate. It had some very far throws, some very short throws, whereas catapult B was much more accurate. It was less variability. It ranged from, 133 to 144, but a huge bulk of its throws were from 136 to 139 is kind of where there's a huge clustering of data there. So, which catapult would I trust more in a pinch? Probably catapult B. So, I know that I just talked a lot right there, and I'm doing that on purpose because when I ask you this on a test or a quiz, that's exactly what I expect you to do. Talk, write a lot. Talk about what you see. Let me know what you see in these distributions. All right, outliers is something else worth mentioning. Obviously, you guys know what an outlier is. It's an unusually large or unusually small data value relative to the rest. So for right now, I just kind of want you to use your eyes, and we'll define it a little bit more specifically later. But if I'm looking at catapult A, I would probably mention that it might have some outliers. It does appear to have a really small throw down here to 120. A very large throw at 155. Could be worth mentioning those things, whereas catapult B doesn't really have any outliers. So make sure you talk about shape, center, spread, and then like a maybe. Like if you see outliers, it's worth mentioning it, especially when you're comparing these two graphs. I would definitely mention the lack of outliers for catapult B. All right, gaps. A gap is a region in a distribution between two data values where there's really no observations. So here we have our stock prices that we saw in another video. And we had a stock price of 108 right here. Here's a 108. And then we had this big gap all the way to 150. First and foremost, a lot of kids think, oh, I don't have to put any numbers here. Like if there's no data there, I don't have to put any stems there. Yeah, you do. You have to go. If you have a 150, you got to go all the way up there, and you can't just skip numbers. So gaps are usually there for a reason. Why is this one stock so successful? What did this one stock do that got so much money? I might want to learn about that. So if you see a gap, I would definitely mention it in the data. We also have clusters. Here's another graph that's bimodal and symmetric, but I might also mention the two clusters. There's clearly a cluster around here, and there's another cluster around here. Now, I know there's no context to this, but this could be something like if I was measuring heights of a large group of people, maybe this chunk down here would be the women, and this chunk down here would be the men, because typically men are higher. Now, could there be a man down here somewhere? Sure. Could there be a woman up here somewhere? Sure. But typically when you're looking at large groups of people, you're going to start to see a cluster for the women and a cluster for the men, especially with something like height, where we know that there are differences between men and women for height. So if you see a cluster, talk about it. So when you see any distribution, make sure you talk about it in context. If somebody asks you, did you go to the store last night? Don't just give them a yes or no. Say, yeah, I went to the store last night. I bought up some milk, and I bought some cookies, and I came home and I dunked those cookies in the milk. I want detail, guys. So when I ask you to talk about data, talk about shape, talk about center, talk about spread, talk about outliers. Do you see a gap? Do you see clusters? And relate it to the problem that you read, because that's what's going to get you a really good grade in this class and on an assignment. All right, that's it for describing what you see in a distribution of data, and we'll do a lot of practicing with this in class.